The following video demonstrates one of the most practical possibilities to violate conservation of energy. The disobeying of energy conservation in electrical systems, discussed here, is inherent in the classical theory but hasn't been noticed so far. There are no moving parts, nor are there messy chemicals as in violation of energy conservation in an undivided electrochemical cell. Thus, observe an electric circuit consisting of a resistor and a capacitor connected in series, usually called RC circuit, powered by a generator of alternating voltage. Pure theoretical analysis of this circuit, not even necessary to be backed up by experiments, proves to be enough for a definitive conclusion that under certain conditions there may be a discrepancy between the input and output energy. That is, that conservation of energy is possible to be violated. Of course, experimental demonstration of the effect shown here will be done in other presentations. But these experiments will only add concrete details to the main conclusion solidly reached herewith. Before doing the actual analysis, it is necessary to emphasize strongly that the part balance of concern for the conservation of energy is only regarding the circuit to the right of the broken line. It cannot be emphasized more strongly that the power necessary to run the pulse generator does not participate in the balance of power when conservation of energy regarding this RC circuit, as well as any other circuit, is examined. Thus, in order to prove violation of energy conservation, it is not necessary to demonstrate a self-sustaining device. That is, device running solely due to the excess energy produced during its action. The big novelty in the discussed way of producing energy is that the energy produced in the discovered here way does not come at the expense of depleting of a previously existing energy reservoir. This is not an alternative source of energy as it is understood nowadays, involving solar, wind, and other energies, which utilize already existing energy by converting from an already existing form into a form to be used for some concrete practical purposes. The discussed energy is not even alternative in the sense Tesla uses the term, because in Tesla's proposals, the energy produced, in no matter how exotic a way according to contemporary science, is still energy from a pre-existing energy reservoir. The energy obtained according to this discovery, alternatively called excess energy or energy out of nothing, does not come about at the expense of a pre-existing energy reservoir. Excess energy in this discovery is produced as a result of saving from the input energy, due to so far unrecognized favorable juxtaposition and interaction of real elements and factors other than energy already available. Thus, the phrase production of energy out of nothing is only a way of expressing that there is no previously existing energy reservoir, but it does not mean that there are no other existing, real, non-energy components and factors, and their respective interactions, due to the approach described herein, which in their totality allow for the production of energy, despite the absence of such energy prior to commencing the process. The method is based on utilizing natural asymmetries, so far unrecognized for the purposes of production of energy out of nothing, which exist in standard classical physics, and concretely here, in the classical theory of electricity. Let us now get into the prerequisites of the discovered production of energy out of nothing, as it were. The current I in such circuit is represented by the first derivative with respect to time of the voltage V applied to the circuit, multiplied by a constant C, equal to the value of capacitance of the capacitor, which we will consider for convenience to be unity. This simple relationship between current and voltage would not have been of much importance regarding conservation of energy, had there not been the remarkable fact that current and voltage are the two components of input power. That is, the two components of input energy per unit time. Furthermore, not less remarkable is the fact that knowing current and the value of the active resistance, R, provides knowledge for the output power, that is, energy, obtained per unit time. Next, we will consider that the voltage applied by the pulse generator is sinusoidal, having the shown form where capital F is the voltage offset. From the illustration here it is seen that when the voltage offset F is 0, the voltage curve is symmetric with respect to the x-axis. Positive voltage offset shifts the curve above the x-axis while negative F shifts it below the x-axis. The character of the voltage applied is such that it will reach periodically its maximum value, V sub m, as time lowercase t goes by, having lower and even negative values in between. To reflect the change in time of the voltage V, we multiply that maximum V sub m by a factor, a function, which has values between -1 and 1, and restores its value of unity only at the beginning and at the end of a time period denoted by capital T. One truly remarkable observation at this stage is that in an RC circuit, such as the one observed here, the capacitor eliminates any effect of the voltage offset whatsoever, and the current is only dependent on the time-varying part of the voltage. That is, if the time-varying part of the voltage is the same, the voltage offset can be of any value, but the resulting current will also stay the same. The voltage offset, that is, the constant voltage part, has no contribution to the current. This observation constitutes a major point in the present study, having far-reaching consequences. However, before considering what effect that fact has on the balance of power, we will observe another remarkable purely mathematical fact. This is one shining example of a possibility to disobey conservation of energy, hidden, inauspiciously, in purely mathematical formulae, which in this concrete case happen to have a direct and undeniable physical meaning. For this reason, let us first observe the average value of momentary sine times cosine product for certain number of points, into which the period 0 to 2 pi radians of these functions has been divided. Let the sine function in this first example have no offset. There should be no surprise why that average sum is equated to average input power P bar sub n. The sine function models the voltage while the cosine function, being the first derivative of the sine function, models the current. Their product is, of course, the input power. In this example, we will calculate the values of sine and cosine of 11 angles, which belong entirely to the overall angle of 2 pi radians of a circle. To do that, as seen highlighted in red, using Excel syntax, the entire angle referring to one period of 2 pi radians is divided by 10. To obtain the increment angle, which is multiplied by the corresponding integer value in column B. Column C contains the values of cosine of the corresponding angles calculated in column A. Column D contains the values of sine of the corresponding angles calculated in column A. Now, column D already contains the momentary values of the products of sine and cosine, corresponding to the calculated angles in column A. The values in column D are in fact the model of the instantaneous powers corresponding to each individually calculated angle in column A. Now these values in column D are to be averaged, so that we can see what the average of this model of the powers corresponding to the period actually is. Excel has a convenient function, average, and its application shows that the average power for the period is practically zero when the sine function, that is the model of the voltage, has no offset. This is seen crudely circled in red. The result obtained is exactly as expected according to the standard literature. Of course, it is easier to see the above result when it's presented graphically. With voltage offset, the only difference compared to the previous example is in column D, the column containing the model values of the voltage. This is an example with negative offset, and again, the difference from the above two examples is in column D. Here we see the power within a period, when the voltage has negative offset. The inquisitive viewer will observe that although the sections into which the period is divided are 10, the number of the instantaneous values of the power is 11. The observer will, of course, recognize that all these 11 points belong to the period. Therefore, the averaging, aimed at obtaining the average power P bar sub n, must be done over all 11 values. The value of the average input power for the period is negative 0.9. This is a truly exceptional result. It shows that the average input power per period is negative when this type of voltage with negative offset, is applied to the RC circuit, invoking the usual current. Same for all examples. Negative average input power means nothing other but that the pulse generator has spent no average energy per unit time for the period as a whole, and the entire input energy has been returned to the generator. And yet, because current has flown through the circuit for that period, energy of the amount of I squared R has been produced in the circuit. Thus, energy has been produced at no expense of the generator, not to say that energy has been returned to the generator in all for the period. It should be noticed that the demonstrated violation of energy conservation is genuine. The necessary condition for that is to actually achieve the discrete signals discussed instead of cherry-picking them from continuous signals. We will not discuss this possibility further because there's an even more interesting possibility to violate conservation of energy even when continuous functions are observed. Firstly, we will note that when continuous functions are observed, then the value of the integral shall is zero for a period because the values of a periodic function at the beginning and at the end of a period are equal, and at the end of the period are using the rules of differentiation. Using the rules of first derivative of f of t under the first derivative of f of t under the differential. This will at once allow, after factoring out the constant 1/2, to apply the basic rule of integration and to obtain because, as said, the values of a periodic function at the beginning and at the end of a period are equal. The same result, 0, is obviously obtained if the periodic function has an offset. We will not show this and will leave it as a simple exercise for those who have any doubt. Therefore, with or without offset, the outcome of finding the value of the integral shown per period will inevitably be 0 in all cases. One may tend to think that the shown integral expresses the mean input power over a period for an RC circuit, to which periodic voltage f of t has been applied, causing periodic current f prime of t to flow through it. This is incorrect. As will be seen, the true mean input power is expressed by a slightly different integral which has profound consequences. To understand how the correct calculation of input power must be done, we start with one already mentioned significant fact regarding the physics involved in an RC circuit, fed by alternating voltage source. Voltage with or without offset always leads to the same non-offset current. In other words, the only factor which contributes to the appearance of current in an RC circuit is the component of voltage varying in time. The constant component of voltage, the voltage offset, causes the flowing of no current through the RC circuit. This figure shows the mutual disposition within one period of the two continuous functions sine t and cosine t. Here we see the trace of the voltage offset by F equal to 0.5 voltage units. The idea is that while voltage offset F plays no role in causing current, only the pattern of voltage change in time being of importance for that matter, offset F should play a role in the determination of power, despite the fact that the numerical value of F itself has no role in the numerical power calculation. The constant voltage, which is the offset part of the overall time-changing voltage, causes no current flow and therefore causes no power input. Therefore, multiplying the current at a given t by the voltage at that t, which includes offset F, will give an incorrect value of the input power, P bar sub in. When considering the role of the voltage in the input power, its offset, F, has to be eliminated, and only the voltage values which belong to the changing voltage part should be used in calculating the input power correctly. Now, if the offset of the voltage is eliminated by just bringing the voltage trace vertically downwards, back to its non-offset reference position, then the initial point, circled in red, of the offset voltage will not belong to the time-changing part of the actually applied voltage anymore. However, it must belong. Only the product at 0t of the current at 0t by the actual voltage applied at 0t gives the correct power at time t0. Indeed, it should go without saying that the real voltage value, or point circled in red as position, should be used in calculating the power, and the only thing necessary is to remove offset. The only trace which can possibly retain the pattern of change of the offset voltage, its time-changing part, losing its offset, that is losing its constant voltage part at that, and having the point circled in red belong to it, that is, the circled in red point being one of the points of the time-changing part of the actually applied voltage, is the non-offset voltage trace shown, phase shifted with respect to the original voltage trace. Notice, shown trace is not voltage which current is derived from. Shown voltage trace only provides the correct voltage values, which the corresponding values of current must be multiplied by, so that correct input power values can be obtained, in consideration of the fact that the applied voltage has offset. Thus, for instance, if the actually applied voltage is 0.5 plus sine of t, that voltage, which otherwise, without the voltage having offset, would be sine of t. Now, when the voltage has offset, must be changed, in accordance with what was just said, to sine of t plus pi over 6, in order for the power to be calculated correctly through integration. Therefore, if input power P bar sub in is to be calculated correctly, the corrected mutual disposition of current and voltage shown here should be used, instead of mere voltage shifted to eliminate the offset. Similar are the arguments in the case when the voltage offset is negative. Notice, the phase shifting of voltage is done only to have the correct momentary products of V times I, and does not mean that a discrepancy in the timing of the current and voltage is introduced. Under the integral, the phase shifting of the voltage only transports the correct voltage value, mindful of its offset, to coincide properly with the current. In other words, in the long run, offset translates as a phase shift of the non-offset voltage when calculating power correctly. Here again we see the amazing negative value of the input energy, meaning that output energy has been produced at no expense of input energy, all the energy from the generator being returned back to it. This is the ultimate violation of conservation of energy when energy, I²R, on the resistor of the RC circuit, is produced by saving of all of the input energy, all of the input energy being even returned to the generator. The generator causes the RC circuit to become a power source returning power, negative IV. At the same time, power of the amount of I²R is produced in the RC circuit. This is power dissipated on its active resistor, R. Notice, once the broken line border is crossed, any power available is set to participate in the power balance. As was already said, no power on the left of the broken line has any bearing on the power balance discussed. The results presented above show for the first time a hitherto unrecognized possibility for violating conservation of energy in electrical systems. Violation of energy conservation in mechanical and electrochemical systems is demonstrated elsewhere. All demonstrated possibilities to violate conservation of energy make it impossible to consider the principle of energy conservation as a universal principle anymore, and the latter must from now on be considered as only an exception. This discovery of the so far unrecognized inherent possibility to violate conservation of energy opens unforeseen far-reaching perspectives for the building of principally new energy generators, as well as an ideological change in all of science, which is probably of even greater importance than the pure utilitarian applications of the discovery at hand.